Lecture number 13 on radiated power. But let me go back to what we ended last lecture. You remember that we were in the process of writing the electric field E in terms of B, and then I found out that by comparing with Manoux, I missed the minus sign, and I could not find it. So I said, exercise, find the minus sign. Actually, right after the end of the lecture, I found it myself. Namely, remember we used this identity. Triple cross product of this is given that. Then I said, let me put this to the other side and this to the other side. That's right. And this, of course, is going to go to the other side. Becomes minus. So that's the minus sign missing here. That is the missing minus sign. So that's correct now. Sorry about it. All right. Now that and so the important thing is that if I know what B is, then I will know E, what E is. So I only have to, in fact, worry about B or E, either one. So let me keep B, expression B here, or I've copied down here. B is equal to this factor, R hat cross this volume integral. And this volume integral would be one of the main characters in this whole discussion. But let me also point out before I forget that both E and B, notice that goes first off with distance, like 1 over R, not 1 over R squared. For the case of time-dependent current, time-dependent source, in fact, the fields falls off like 1 over R and not 1 over R squared, and that's important. All right, and now I'm done with this. I need a blackboard space, so may I erase all this? I've kept this here already. Okay, we have worked out E and B. So now, in fact, we can talk about power of radiation. And to do that, let's remember that that's given by the Poynting vector, which is 1 over mu naught E cross B. And as we saw, E cross B would point in direction of R hat. That's to be expected. That's where we look for the observation. So this is so let me look at the magnitude. Since it's in the R hat direction, so let me start it with R hat. So what's that? There's 1 over mu naught E cross B dot with R hat. And I can make use of vector analysis. Let's see. So to write this as mu naught, over mu naught R hat cross E dot B. Correct. But R cross E, R cross E is nothing but B after the factor of C. So this is C B. So this whole thing is given by C over mu naught times B squared. And once we have B, then we can write down power, quotient a unit area. So this is nothing but power per unit area. This P here stands for power. Radiated energy per unit time. This is the area. So this is what we have here. So C over B mu naught B squared. But more useful than power per unit area would be the angular distribution of power. Namely that we notice that if you draw from the source at this point, we draw the A. in this direction, then of course it subtends a solid angle d omega. And this distance is where this dA is r. So that dA is equal to r squared d omega. D omega stands for differential solid angle. R squared d omega. So that, okay, what I have is the following. So that dP d omega would be r squared times b squared. And you notice that that's a good thing to do, because this r squared will cancel this one of r, whole thing's b squared. So this would give me c over mu naught. B is here. Cancel this now. I have mu naught over 4 pi 1 over c squared. Right? I was going to cancel mu naught over c squared. Then times the square of r hat cross this volume integral, which is the main character in this discussion of r prime at the retarded time square. And we can simplify this as 4 pi square, mu square, so that that's for the mu naught, and then this what the c. So that we have the power per solid angle is given by, let me copy down here, given by 1 over 4 pi squared mu naught over c. Have I missed anything? For mu naught square, correct? Times r cross this quantity, the volume integral, square. All right. And of course, the total power of radiation will be the integration by this, well, we can integrate over solid angle. And then the power of radiation is d omega integrated over theta and phi. d omega. D omega, of course, is nothing but sine theta d theta d phi in terms of the polar angle and the azimuth angle. All right? So now let us work out an example of power radiation. The simplest example would be involve just a point charge, just one particle. So, and I'm done with this. So I need blackboard space. So let me try not to touch this part. Okay. I can erase this. All right. So let's say that we have point charge, charge Q moving with velocity v, but with a speed much less than speed of light. Okay. So that the current for this is given by Q V, and let's say that, and so we are interested in the current at TR. And, all right, TR, you remember, is given by T of a surface minus R of C plus this term. But to the lowest order of approximation, we can ignore this term, small correction. So let me call this combination of T and minus R OC to be TE. So this TE plus this additional small term, which I will come back to talk about later. So this is my TE. So let me talk about the current at R prime, at R prime, at T prime. T prime I will later use just this TE. TE is most, I call emission time, it's close enough. Okay. To the lowest order of approximation, this is the emission time. So this is equal to QV at T prime. And let's say that at T prime, this particle is at the location big R at T prime. Okay, in that case, now we can calculate what this is. The volume growth of del by del T, I can pull outside. It can become d by dt. And times J of R prime T prime. This point. Okay. And so this would be d by dt without time. And now approximated as emission time. This volume growth will take care of this delta sign. So I'm left with d by dt acted on Q V evaluated at the emission time. And I can approximate this return time by the emission time because this term is small. This term for this problem, of course, is given by R prime is my big R. Is given by R hat dot this big R over C. So since we're talking about a slowly moving particle, so that the range, so that its location will be confined. It cannot move too far away. So that's why this R prime small, this term small, so that I can approximate, TR, the return time by just the emission time. All right? Good? So then now we have this. And what is the power of radiation? The power of radiation is given here. D P by D omega. So this gives me the angular distribution of the power of radiation for this moving charge. And that is given by 1/4 pi square, which is 1/4 pi by 1/4 pi. Then I have mu naught over C times R hat cross what I have here, cross I can put it, let me put dV by dt evaluated at the emission time. This whole thing square. By the way, we can integrate over triangle to get the total power of radiation at time t. So that would be, let me write this as, let's draw this. So this is, let's say that this is the direction of observation, R hat. And let's say that this is the direction of dV by dt at the emission time. dV by dt at the emission time. dV by dt, of course, has the meaning of acceleration. So this is the acceleration of the particle at the emission time. The angle between R hat and this, let me call it theta. So this is nothing but, this dV by dt evaluated at time of emission square times sine square of this angle, theta. And now we can get the total power of radiation by integrating over this proper triangle, so that we encounter sine square theta d omega integrate. And let me so this is nothing but sine theta d phi. Let me leave it as an exercise for you. Let me normalize it to 4 divided by 4 pi. Without sine square theta, that of course is 1. With this factor, sine square theta in integrand, let me leave it as an exercise. For you to show that it is 2/3. So that, when I integrate over a certain angle, this eventually becomes 2/3. So that when I integrate over a certain angle, that's a factor 4 pi, cancel this 4 pi, so there's only 1 factor 1 over 4 pi. Then I have mu naught over c times this times 2/3 of this dv by dt squared at the emission time. That is what it is. Okay. One thing to notice is that for the power to be non-zero, dv by dt got to be non-zero. And in other words, a non-zero dv by dt implies that there is power of radiation. That means an accelerating charge radiates energy. That's important. And accelerating charge leads to radiation. So if you have a particle going around in a circle, like in a cyclotron or a synchrotron, it radiates energy. So that means it loses energy. So if you don't want the particle that you are studying to lose energy, for it to keep it to go around, a circle would not be a good idea. In fact, that's one of the reasons why people developed the technique to do linear acceleration instead of circular acceleration, linear motion instead of circular motion. That's why there was, there's the Stanford Linear Accelerator Center. All right, so much for this. And I don't think I have to keep this here. So now let's take my slow discussion to a bunch of particles, charged particles, all of them moving slowly, so that I can, for the whole system, I can replace the retarded time by the time of emission, T. So, now we are left to study this guy for the whole bunch of particles. Let's see what we get. All right. So I'm interested in the volume group of del by del T, J, and R prime. Evaluate the whole thing at emission time. And let me put this d by dt out. So d by dt, and I will be the derivative was te. So let me put it here. d1 prime j of r prime at te time. And now I have to do this for the system under consideration. How do I do that? There's a trick to do that. And may I erase this? Oh. Uh, yeah, well, I can do this. Oh, sorry. Notice that the power radiation is proportional to sine squared theta. So if theta is 0, there will be no radiation. That means that if the direction of observation is along the acceleration, then you would have no radiation in that case, in that direction. All right. How do I do the volume integral of a general current density? Well, let me start with conservation of charge. So that I have divergence of J at R prime. Let me keep TE understood. That is equal to del by del TE of TE, rho of TE. And so that if I take the difference of the two, that would be 0. And if I multiply by R prime, that's still 0. And if I take the volume integration, that's still 0. Okay, now let me take a look at this term. What will give me? Well, this term will give me something simple. So that's minus. Okay, let me put the del t outside. So give me d by dt. 1 of r prime rho. At R prime G. So that's what this term gives me. How about this term? This term is nothing but the one of the following. In this expression, I have R prime times divergence of J. So that this gradient acts only on J. But let me in fact move this gradient to the left side of R prime. So it acts on R prime also. So I will have divergence of this. That means scalar product of this grid operator vector and J. So I better keep that. So J is standing next to gradient, then R prime. So then now this grid operator acts on J as well as on R prime, and as a dot, you have the scalar product of this dot with J. But of course, I've done too much derivative. In addition to grad prime x on J, I also x on that. So I have to subtract that off. So that would be minus J. What I mean is that, so we have, this term corresponds to J dot this grad. If the dot's always between grad, then acting on R point. And this is just a unit dielectric. By that I mean, if you take a look at this, well, at the ith component, ijth component, this dielectric, grad prime R prime. Let me look at it. Involves two vectors. So let me talk about two. The ith component of grad prime and jth component R prime. What's that? I claim that that is nothing but unit dielectric ith component, which is nothing but the conical delta function. And this, of course, is ith component. This is nothing but del prime I R prime J. This, as we know, of course, it's not nothing but del I J, so it's consistent. So that this term, what I'm saying, so this term correspond. This term is this and that. Subtract off, because this term comes from this. Okay, j dot the unit matrix x like 1, so it's just j. And okay, so these two terms combine to be 0. But this is the one integral of divergence. So the Gauss theorem tells you that this is nothing but surface term. But j is bounded in the volume, so that this term, the surface term, goes to 0. So that means that this plus that is equal to 0. So that I can write this as j equals to the other side. So j, the volume integral of j will be equal to minus d by dt, the volume integral of rho r prime rho. Volume integration. What's that? That, of course, is nothing but the electric double moment of the system you're talking about. P. Okay. At the emission time. So that this is right. So this is P at t time, and I would write d by dt denoted by a dot. So minus P dot evaluated at emission time. It's understood. So that's what it is. So this is, let me write this down. To the lowest order of approximation is nothing. So let's see. So this is, one derivative. That's another derivative. So that in fact, this is equal to minus P dot dot. One dot stands one time derivative. That's one, and that's this one. For the one integral of the derivative of j, just P dot dot. And let me check against the note to make sure that I got a sign right. Is it minus P dot or oops. I did not even write it down explicitly, but minus no, that's a mistake again. Oh, there's a J here. Minus. Wait a minute, that's correct. Oh, sorry. My mistake again. Luckily, I checked the sign. Conservation law. I'm so used to that. This one is equal to minus this one. In fact, when you put it together, there's a plus sign. Oh, terrible. So that this is plus. Yeah, I thought, remember, it's plus p dot, not minus p. So in fact, it is plus. Sorry. All right? In this approximation. Okay, so that the expression for this b is minus, so this is, well, this is p dot here. And again, do same thing here. And so this is my, so then let me write down, the power per solar angle, will be given by this times result. So let me, for the small system that I'm talking about, the contribution is proportional to, P double dot, don't forget, evaluated at T. So that I have, dP by d omega is equal to 1/4 pi squared mu naught over c times the square of r hat cross my p double dot. Understood to be evaluated at the emission time square. Okay. So, okay, let me write this down. So this is equal to, okay, 1 over 4 pi square mu naught over c of r hat cross, okay, p double dot. Let me leave some space. Square. All right? And also, okay, since this has been evaluated to be p double dot, I can write my p, manipulate p to be minus mu naught over 4 pi 1 over r c r hat cross, okay, p double dot. I will leave more space here. Okay. And this one is, okay, given by r cross, so I have vector minus, so let me work out r cross b. So r cross b, let me look at this okay, vector. So I have, okay, r hat cross p double dot. What's that equal to? Well, there are two terms. Okay, one is, okay, in this direction is minus p. I'm sorry. How about, okay, whole thing square. I was working out r cross b. So here, so r, this one cross b vector involves this r hat cross this. So that I have, okay, minus p double dot times r hat dot r hat is 1, then plus r hat, okay, r prime r hat dot p double dot. Okay. So this is my, okay, that is, okay, this r dot dot. So this is equal to, okay, minus plus, c cancels, so mu naught over 4 pi 1 over r, okay, of, okay, minus p double dot plus r hat, okay, r dot p double dot. Somehow there seems to be something not quite right. Let me look at my notes. Where have I made a mistake? Oh, I haven't made a mistake, but actually, in fact, it's better to keep it in the original form. Okay, that was my mistake. I've done too much. So, this one. Let me, okay. So, cut down the one, right one. So, 1 over 4 pi, okay, this one, 1 over r, and r hat cross this r hat cross p double dot. All right, unless I've made a mistake somewhere. No, I think this is it. C cancel the C, so that and plus mu dot over r. So r cross r. I think I'm right. Okay. I've left some gap here because I'm going to, in fact, okay, calculate, okay, the next order term and incorporate it in this species. All right. So then now, okay, obviously, okay, we can do the integration of a solar angle to give me the total power of radiation for this system consistent of, okay, time variant, okay, electric dipole moment, P. In fact, accelerated rather no movement. Okay. So this, of course, again, okay, would involve r dot cross r hat. That will introduce sine square. Okay, sine square integrate out. Okay, would be average to be 2/3. So this is equal to 1/4 pi 2/3 mu naught over c. Okay, r mp double dot at t square. All right. And what's next? I should consider. By the way, okay, here in the lecture, I have this factor, okay, mu naught over c. But okay, in my lecture notes, okay, I use instead 1/epsilon naught c cubed. Okay. It's easy to show the inverted the same. All I have to do is multiply both upstairs and downstairs by mu naught. This mu naught, epsilon naught is nothing but the reciprocal of c squared. So this in the denominator cancel two of them. So giving you this. All right. So it doesn't matter how there are many ways to write this. Mu naught over c. All right. So and okay. So this is general for system with electric double moment P. So this would then be the power of radiation. Of course, if the system consists of only a single particle, then you should get back what we talked about before for a single particle. But in general, P will be given by sum over contributions from the different charges, say Qi, Ri, sum over I. And then this P dot dot would be sum over I of Qi, Ri double dot, the whole thing squared. I would like to point out that it's the square of the sum of terms. So that means that there will be interference between different particles. I just want to point it out. All right. And it's now time to do the next thing. This is important. And what should I? Okay. I think I've filled up all this. Now it's time to move on. To go back to the general expression for this. In the time dependence appears as retarded time, not emission time. So and they differ by this small term. And let me make a tail expansion to include this term. So that's the next contribution. Here is this. Okay. So what do I want? So let me consider this. Oh, I use this symbol. So let me in fact not use this notation by using this. So this one integral is equal to one integral of j at r prime and at oops. Now, this okay. I have used this TE. So let me work this out for the TR. Well, let me just do what's written down here. So that I'm interested in the one integral of the time derivative of j and R prime, and the return time, which is the emission time, plus this bit, plus R hat dot R prime over C. So this is the second time that I have included the effect of this term. Remember the first time I included the effect of this term is in fact in last lecture, where I would like to make use of conservation of charge. And then it turns out that that contribution cannot be ignored in order to have conservation of charge. All right? So this is what I want. This is that important thing. This. All right, as I said, let me put this d by dt outside. So this is d by dt. D by dt, put outside the y integral of this. So the first term, of course, would be current density at R prime at time being the emission time. Then I make tail expansion, So what's that? Then plus, this additional term, so we'll be R hat dot R prime over C, del by del T of, J at R prime evaluated at emission time. This term is in the time dependence. The argument corresponding to time dependence. So the time dependence is TE plus this extra. So this extra give you this term times del this has been moved outside of this. So it's del by del T. So notice that for this term, there were two time derivatives. All right? So that, we are, this term, we have done that already. What's that? This term is nothing but, this term, of course, is this term. This term, the order I'm looking here is this. And this is P dot. So that I have P. This is P dot. So that I have this is in. So this is gives me P dot, another derivative, so it's P double dot. Then I have plus d squared by dt squared acting on, these are constants, so it can be, put outside, oh, wait a minute, what integral of R prime, I have dot, what do you see, of, I put out this del by del T outside already, so that I have R prime J. And this dot here stands for the scalar product of R hat with this R prime vector. The vector that stands next to the dot. All right. And now, what do I want to do? Now let me, in fact, write this term as 1/2 of R prime J plus R prime J. So this is product of two vectors. So it's a diagonal. So this is half of one of them and another one. Here, let me put minus J R prime. Then there will be plus J R prime. notice that this order is R prime J, this is J R prime. They're not the same. Okay. Let me take a look at this combination first. And then I will deal with this one. It turns out this term is small compared to this term. Yeah. This term turns out to involve electric quadruple moment. Which is one higher moment than electric double moment. And we'll be interested in only keeping all these contributions up to the dipole moment term. We're interested in contribution coming from electric dipole moment and, well, there's another dipole moment, magnetic dipole moment. I'm going to show you that. This corresponds to contributions from magnetic dipole moment. This corresponds to high moment in the electric case. So, we will not be keeping this term. And I will indicate why that is so in a moment. But at this point, let me, in fact, do this term. And so what's that? So let's see. So I have here this. Oh, let me just, without the D double, just do this. So, this obviously is 1/2 of the one group of, and that's the 1/C, and of, let me see, this, let me do it, be careful. So let me omit this 1/2 C. So let me consider R hat dot, R prime J minus, R hat dot J R prime. What's that? That looks like a triple cross product. Namely, that is equal to, this is in the direction of J, this is in the direction of R prime. So this is J cross R prime, R hat cross that. So the two terms in this triple cross product, one in direction J, and this given by multiplied by R hat dot this. Another one in the direction R hat, R prime is multiplied by this dot that. That's correct. So this is equal to that. And so let me put this to the other side. So that I have minus sign, minus, minus, interchange this two, minus, and I have this R hat, this cross. This cross stands for the cross product I have, and what else would be a vector here. And that vector is, I have interchange, let me interchange this to an expansive minus sign. So it's R prime cross J. I think I got it. Now, what is 1/2 Van der Graaf of R prime cross J? This is the magnetic dipole moment of the system. M, magnetic dipole moment. And you may not have encountered this form of expression for magnetic dipole moment. I think the magnetic dipole moment expression you have encountered is something like 1/2 of line integral of let's see R across dl and times integral current. But of course, since in the line in the circuit dl is in the same direction of I, so you can write this as 1/2 dl of R cross I. This is the expression of magnetic monopole for a circuit that you have encountered. And okay, in this form, okay, you can easily generalize it to a volume integral. All you have to do is okay, replace okay, the line integral okay, by the volume integral, and okay, at the same time, okay, replace this line okay, current by okay, volume current. So this is okay, nothing but we have here. I use the prime variable, and this of course is our point. So that in fact, okay, this is nothing but the magnetic dipole moment of the system. So that okay, I have now okay. Let me show this in a moment. So this is equal to P double dot plus or minus rather, and I will check the sign in a moment against my notes. I think I'm correct, but who knows? I've been careless. Minus, okay, double derivative. So okay, minus. This 1/2 is included in the definition. So minus okay, R hat cross M double derivative. So that everywhere I see P double dot, I can replace by P double dot, okay, and this. So here I can include the contribution coming from okay, the magnetic dipole moment, okay, by including this term minus R hat cross M double dot, and here, okay, minus R hat cross M double dot, and here, okay, minus R hat cross M double dot. And let me check against my notes. This is 1 over C. I've forgotten. 1 over C. Yes, this is 1 over C. See, this good thing that I checked. 1 over C. What else? Any more mistakes? Okay, correct? All right. So that, and here, this is okay, minus R hat cross 1 over C M dot. All right. And let me show you that this term, in fact, okay, corresponds to electric quadruple moment. Okay. And in case you have never heard of electric quadruple moment, okay, you remember double moment is moment of okay, charge. P is equal to 1 integral of okay, this times rho, moment of charge density. And now, okay, let me talk about okay. So that there's one index, Pi. Double moment carries one index, is a vector, whereas quadruple moment, in fact, is a dialectic, carries 2 indices. And let me just tell you, that's the case. Okay? I don't think I would want to repeat the calculation, which okay, when I taught okay, 311, I included the discussion of quadruple moment in my course. But that might not have been done in your 311 course. But let me just indicate that that indeed corresponds to the okay, electric quadruple moment. Let me erase this. So this is just for your information. I'm not okay, really okay, deriving it from scratch. Okay. The electric quadruple moment, as I said, is static. It carries 2 indices. Okay. This is roughly. Sometimes people define it 1/2 or not. 1 integral of okay, R J. Okay, that's vector of 3 minus delta Ig. Okay, times charge density. Okay, this is okay, the Ij okay, component of this okay, electric quadruple moment is this. Okay. And let me show you this term. In fact, this term I will not consider because in fact this term, if you do the calculation, this term doesn't contribute anyway. So let me show you that this has to do with this part of the electric quadruple moment. And the way to do this is, so I'm interested in the volume growth of this R prime J plus J R prime. Oh, just erase this. And I have, okay. So let me in fact talk about the ijth component. So prime I J. So I get moment of this one. And so what is that? Oh, a moment for. Okay, that is the integral I want to calculate, and I claim that this can be written as one integral of let's see, R prime I, R prime J times the divergence of J. That's my claim. And that's the question mark. Okay. And let's see, this gradient x on J, but you can integrate by part. If you integrate, integrate by part, so that this gradient x on Ri, Rj. So let me consider R, x on Ri first. Okay, when the x on Ri, they will give me delta ij, they change this to the I. So they will give you Rj, Ji is this term. But if this gradient x on this one, then you will give this term. Okay, and since there is integration by parts, so there's a minus, doesn't matter. On the other hand, I can for divergence J, I can use equation of conservation charge to write that as minus del rho by del T. So this is equal to minus plus d del t push to the other side. So that will have one integral of R I this term exactly. Okay. I'm sorry. So this del T rho, right? Okay. So this is I'm sorry. Here R I prime J times the charge density. This, you can see, is, where is it? After a factor of 3, is this term, first term of Qij, the electric quadruple moment. As I said, this term turns out not to contribute, affect the argument. So indeed, this term refers to electric quadruple moment, one moment higher than double moment, so I'm not going to consider it. So that's it. All right, I have 10 more minutes. Let me see, where should I go? Okay, so far, I want to finish this up before next time. So let me erase all this and come back to talk about power of radiation. So let me come back here. I have dP by d omega, angular distribution of power radiation is equal to this 1/4 pi square mu naught over c times the square of this. Square of this. Let me copy that down. So that I have R prime cross P double dot, okay, minus R hat cross R hat cross M over C, the whole double dot, whole thing square. Obviously, okay, there will be three terms. Okay. One has to do with square this, so give me R hat cross P double dot square. And then square this, okay, and this cross R hat, so that think of this as a certain vector, okay, and cross this R hat, take square. The cross here gives you the sine of the angle between this vector and this vector. But since this vector is orthogonal to R hat, so the sine of the angle between them will be 1. So that the square of this is just the square of that. So minus, to the square. Okay, so plus R hat cross M from that C square. That's simple. Now the complicated part comes from the cross term. So there's minus 2 of R hat cross P double dot, dot with R hat cross M double dot over C. This is complicated, but this is the cross triple product, can be written in terms of two terms, one in 1,000 R hat, and multiplied by this dot dot, so it's R hat dot M double dot over C, minus, in this direction, M double dot over C, times R hat, dot R hat is 1, so it's this. And I'm supposed to dot these two terms with that term. This term is orthogonal to R, dot this term is down to R, but this will not continue. So that I can rewrite this second term as minus is plus 2 1 over C of R cross P double dot M double dot. Isn't that right? Minus and plus. Okay. And this I can write as, let's see. Let me see how do I do this. This double dot goes M double dot. So that I can write this as R hat dot P cross M, if I'm not mistaken, in quickly doing the algebra. I'm correct. So this term is given this three terms. So so let me recopy this as this. This 1 over C R hat dot P double dot cross M dot. So in the angle distribution of power radiation, there's a cross term involving both the electric dipole moment as well as the magnetic dipole moment. But if you are interested in the total power of radiation, then of course here, since this dot, that means that that will involve cosine of a certain angle, not square. So that upon integration, this would drop out. And all these two involving square of cross product involves square of sine. Sine square integrate to be 2 pi. I mean 2/3. Okay, so this is equal to Okay, integration over the angle cancel 1 of the 4 pi, so it's 1 over 4 pi. Mu naught over c. Okay, times 2/3 of p double dot square plus 1 over c square, okay, m double dot. And again, check. Yes, correct. All right. And at this point, a little bit more than 5 minutes left. Okay. So let me finish it up. Okay. By filling up this. So the B now is given by this. Okay, correct. And E is given by that. And this is the complicated term. Let me simplify this term. Okay. Let me simplify this term. Okay, I've done this already, so okay, I'm not going to do it. Okay. So then, okay. So this should be one of the expressions recorded here in this table. But I don't have space there, and I don't have the time now. So let me simplify this term. I do it very quickly. So I have here, look at this, it's turbo looking. It's R hat, cross R hat, cross R hat, R hat, cross M, double dot. Let me forget about my sign and one of C. And what is that? Well, it's in fact not terrible looking. So this is, okay, now it's R hat cross. I can use the triple cross product to work this out. There's a term in direction of R hat multiplied by R hat times M double dot. And then there's a term in the M double dot direction with the minus sign, then R hat dot R hat is 1. So this is minus M double dot. Lo and behold, the complicated term here involves is in direct R hat, but cos R hat. So this term is not there. So that this is in fact quite simple. Okay, this R hat would be just R hat cross M double dot. So well, I do not have time to finish up the calculation. So I can ask you to to write this, simplify this to be this aside from the factor of C. And then you can be able to show that. Let me just give you the result. We are not it's E is given this term, then it turns out that this term is this. Cross P dot plus, I hope the sign is correct, minus, I think I'm right. Yeah. And this term is simplified to be this M double dot cross R is here already. So it's M double dot over C. R cross R plus this, yes, correct. And what else? D is this R plus correct. So this correct, and this we have worked out. And total power radiation is given with this. And this important time derivative. I mean, for me, integral of derivative of the current is given by this term and this term, both involving double time derivative. All right. at this one, I should in fact, give an example. And I do have an example in my lecture notes. And so we will stop here and work out that example very quickly at the beginning of next lecture. In lecture number 14, this is lecture number 13. So let us stop here. Good thing that I have not made too many mistakes. All right. So, I can erase this. And then let me keep this on the blackboard for next time, to use for next time. So right after, we take care of that example, we will go on to the last chapter of the book. We'll be talking about special relativity and its connection with electrodynamics. Special relativity normally is taught either in a course on mechanics or in E&M, and you will see why, in fact, it is logical also to talk about special relativity in a course on electrodynamics. There's a strong connection between the two. In fact, one time, someone said this to Einstein, and the person said, "Oh, Albert, you're so lucky. You stand on the shoulder of Isaac Newton." To which Einstein was reportedly said, "No, actually, I stand on the shoulder of Maxwell." So he considers his theory of relativity to be more connected with electrodynamics than non-relativistic mechanics due to Newton.